$200 million. That's the amount of money that was lost from one instance of credit card application fraud in the United States in 2013. Just from one instance, they lost $200 million. Actually, one person was able to lead a whole group and actually obtain 7,000 fake identities and 15,000 illegal credit cards. And how are they able to do this? Well, in their credit card applications, they actually used other people's personal information, and they were able to get credit cards based on that. And so illegally obtaining credit cards is actually such a big problem. In Canada alone, Canada's cumulatively lost $800 million due to credit card fraud. Now, realizing what a big issue is, it's so important that we find a viable solution. And using one of the most powerful technologies that we have, we can solve this problem. Machine learning. Using machine learning, I was able to create a model combining a deep learning model called self-organizing maps and artificial neural networks to generate a list of customers based on how likely they are to have committed fraud in their credit card applications. And there's two steps to how I did this. I used a self-organizing map and an artificial neural network. But most of us already know a lot about artificial neural networks, so I think we should focus more on self-organizing maps. So we know that machine learning can be divided up into three subsets: supervised learning, unsupervised learning, and reinforcement learning. Self-organizing maps are actually a type of unsupervised deep learning. And so what that means is that when we feed data into our model, our data is actually unlabeled. So if I were to feed a model an image of a cat and a dog, I wouldn't explicitly label that image as a cat or a dog. You let the model itself determine and organize the data so that we can make meaningful conclusions from it. And so we have self-organizing maps, and we also have artificial neural networks, which work really well for the most part. So why even care about self-organizing maps? Well, actually, like most deep learning models, artificial neural networks actually can't take in multi-dimensional data sets. And that's one thing that self-organizing maps can do. They can take multi-dimensional data sets and convert them into 2D matrices, which they can actually use to organize data. And so here's an example of a self-organizing map. Here we have 39 indicators in our data set, all of which contribute to the quality of life of a nation. In the top left, we have the orangish yellowish colors, which sort of indicate that a country has a high quality of life. And then near the bottom right, we have countries which have a low quality of life. And we have sort of two extremes over here. We have countries with a high quality of life and countries with low quality of life. And then sort of the countries in the middle, in the greenish and the purplish areas, are countries that have a moderate quality of life. And so this is just like a visual example of how self-organizing maps work. And then here's the same self-organizing map on a world map so we can visualize our results. Now, the question is, how are we going to get from our multi 3D, 4D dimensional data set into something like this? And so to really understand that, we need to know how self-organizing maps actually learn. So here's an artificial neural network which we can use to kind of visualize how self-organizing maps work. We have two layers, and this artificial neural network is actually quite deceiving. In our input layer, it seems quite small, but actually, we know that our input space is actually three-dimensional. So we have three different columns, but underneath each one of these columns are actually hundreds of rows. So we have a bunch of data, but we just can't see it because it's in a 2D surface. And then we have our output layer, which is always two-dimensional. So here are a few clarifications we can make to distinguish between an artificial neural network and a self-organizing map. Well, for one, we have weights, which are the lines that connect layers together. And in self-organizing maps, they are indeed called weights, but they actually serve a different purpose. In SOMs, or self-organizing maps, we actually have these weights actually are the coordinates of each node in the input space. So given here is the coordinates for the first node. And so there's three nodes, since there's actually three coordinates per node because it's in a 3D space. And then we can do the same thing for the rest. We can do the same thing for the rest of the nodes. And then now what we actually want to do is think of this as a competition. There's actually there's hundreds of rows underneath each column of our data set, and each one of these nodes is trying to compete for getting the most accurate results. And so one thing that we can do is calculate the distance between these nodes and the rows in our columns. And so one important clarification to make is that self-organizing maps actually don't have activation functions. And so as a result of that, we need some way to tell the self-organizing map on how it can organize the data. And so that's finding the closest distance between the node to a node and to a row in our data set. And so we can calculate it by getting the value of one of our input nodes to a weight of another node. And we can, since each node in our output layer actually has 3 different weights, we can do that 3 times and find the difference between those 2 values. Then we can square them each time and add up all their sums together and square root and do the square root of that total sum. I know that's pretty complicated, but just bear with me here. Okay, now we found the total distance, we found each distance. And now once we find the shortest distance, we can actually, we choose the one with the shortest distance. And in this case, 0.2. And that's actually what we call our best matching unit. So that's what we're actually going to use. That's what actually the self-organizing map is going to emphasize when it's organizing its data. And so here's a more visual representation to help us understand. Our best matching unit of 0.2 is on the grid over there. And it's basically represented by the green circle. And now we have another best matching unit if we did the same calculations for another row of our data set. And now once again, it's sort of like a competition. All of these circles actually represent data points from our data set. And so these nodes are actually trying to drag as many data points as they can closer towards themselves. And so what defines success in this competition is being able to drag as many data points towards the best matching unit as possible. And so, but one limitation is that each of these best matching units actually have radii. And so what happens is that it can only drag data points that are in its radius. And so the closer a node is within a best matching unit's radius, the more that it'll be able to drag it. And so here's a way to help us understand the dragging process of best matching units. And so on the image to the left, we actually have the white dot is represented by our best matching unit, and the yellow circle represents the closest point to our best matching unit, and it's dragging the closest point. It's actually only dragging 1 point, but as a result of dragging 1 point, it's actually dragging all the other points along with it, but again to a great lower extent, which just emphasizes that when data points are in a best matching unit's radius, the closest points are actually dragged more than the ones that are further away. And then now let's take a look at another point. Because when we're actually organizing our map, we want it to look like the image that I showed you at the beginning of the presentation. So we need to color all of our grid. We need to color all of our circles. And so the one that you see there with the arrows pointing at is actually one that's been colored. And this one has actually been mostly influenced by the blue best matching unit more than the green one. So it's more of a darker shade of blue. And then now we can see that the radiuses overlap, just to emphasize that while both of them are actually while both of them are actually pulling the data point together, the blue one has more of an emphasis. And then now we just have more points just to emphasize the result of what a self-organizing map can do. So we have different shades. And then now let's go over what happens if there's actually more than 2 best matching units. And this is the case with most self-organizing maps. And so there's actually hundreds of best matching units that we can occur, but obviously we can't fit that all into one slide. And so now if we have 4 best matching units, they all have radii. And so what happens now is that each one of them are once again dragging as many data points as they can towards each other. But what happens in this case is that the radii actually gets smaller as we go through more epochs. And an epoch is essentially just iterating through the model iterating through the data set once. And now here's a visualization of that. There's actually now, as we want to move our data points closer to the purple area where we have our best matching unit, initially we drag the data point really by a great distance because we know we just want to get into the general area. But as we get closer, we want to make our movements a lot more accurate, and so that's why we want to make our movements a lot more smaller. And so by having smaller radii, we can move our best matching units a lot more accurately. And now here's the final result, just emphasizing the final result of what a self-organizing map does. And now here's the actual self-organizing map that was printed in the Python console. And so the red circles and the green squares represent the best matching units. And so those are the ones that we actually care about. And so the green square actually represents customers whose credit card applications got approved, and the red circles represent this customers whose credit card applications got denied. And so those are the ones that we care about. And on the y-axis, we have values for probabilities. And so if they range from 0.2 to 1, and the higher the probabilities get, the more likely a customer is have to commit fraud. And now if we focus on the squares that actually have winning nodes on them, we can see that the lighter ones are the ones that we have to emphasize ourselves on. And so as a result of that, we know which customers actually have committed fraud, which customers are more likely to have committed fraud on their applications than others. And now here's the final result of what happens. So we have a ranked list from lowest to greatest probability on how likely a customer has on committing fraud. Now, keeping all of this in mind, it's so important to realize the large scale of this problem. And so, using machine learning, we can solve this problem. And even taking one step at a time can make a huge difference. Thank you.